Hello everyone, welcome back to the channel Future Force. Today we are diving into a weapon that has long straddled the line between the realm of science fiction and real-world military technology, the railgun. For decades, military engineers, defense analysts, and even movie directors have been fascinated by the idea of harnessing electromagnetic energy to hurl projectiles at blistering speeds. The concept is as thrilling as it is ambitious: no gunpowder, no explosive warhead, just pure kinetic force smashing into a target at hypersonic velocity. The railgun has been called a game-changer for modern warfare, a symbol of the future battlefield, and the ultimate high-tech deterrent. But behind the hype and dramatic demonstrations lies a far more complex story. Is the railgun really the breakthrough weapon of tomorrow, or is it an over-engineered, over-budget, and underperforming dream that will never truly leave the prototype stage? In this deep dive, we're going to explore every aspect of the railgun, from its commanding exterior presence, the intricate components hidden inside, and the raw performance metrics that have stunned observers, to the safety measures, unique advantages, jaw-dropping costs, and a sober assessment of whether it deserves a place in the future arsenal. The first thing that strikes you when you see a railgun in person is its sheer size and imposing design. Mounted most commonly on the deck of a naval destroyer or test platform, the railgun is not a compact weapon. Its barrel, often 6 to 10 meters long, is straight and industrial, lacking the rifling grooves that traditional cannons possess. Instead, the exterior looks smooth yet reinforced, with a noticeable rectangular or trapezoidal cross-section in many designs, which hints at the unique internal rail arrangement. Surrounding the main barrel are support structures that house cooling lines, electromagnetic shielding, and mounting brackets that secure it to the ship. Behind the barrel, the housing for the capacitors and energy storage systems is large and blocky, sometimes as big as a shipping container. This back section is where much of the weapon's magic and weight resides. The exterior is usually finished in matte naval gray, though test units sometimes feature black or metallic accents, and certain experimental models have exposed components so engineers can observe them in operation. When viewed from the side, the silhouette of a railgun looks different from any other naval weapon, more like a blend of industrial machinery and a futuristic cannon from a science fiction video game. The minimal moving parts and linear barrel structure give it a distinctive, almost alien appearance compared to the more rounded shapes of conventional artillery. Inside, the railgun is surprisingly straightforward in theory, even if building it in practice is anything but. The heart of the weapon consists of two long, parallel conductive rails made from high-strength materials, often copper alloys. The projectile sits between these rails, and when the capacitors discharge, a massive electric current flows through one rail, into the projectile, and out through the other rail. This creates a powerful magnetic field that pushes the projectile forward at extreme speeds. Surrounding this assembly are the capacitors, power converters, and control electronics that manage the precise timing and energy release. Insulation is critical, because the voltages involved are enormous and even a minor electrical leak could cause catastrophic failure. While the actual mechanism for launching a projectile is elegantly simple from a physics standpoint, the supporting systems, including cooling, alignment, and diagnostics, are densely packed and meticulously engineered to handle the incredible stresses generated during each firing. Performance is where the railgun truly captures the imagination. Traditional naval guns rely on chemical propellants to generate explosive force, but this has limitations in terms of speed and range. The railgun replaces explosives with pure electromagnetic acceleration, propelling a projectile at speeds exceeding Mach 6 or Mach 7, more than 2 kilometers per second. At these velocities, a projectile can travel over 100 nautical miles and still hit with devastating force. Unlike a missile, which relies on a warhead to inflict damage, a railgun's projectile carries only kinetic energy. When it impacts a target, the energy release is so intense that the target can be shattered or punctured without any explosives at all. This also makes the weapon theoretically safer to operate, since there is no risk of onboard ammunition detonating due to enemy fire or accidents. In tests, railguns have demonstrated the ability to strike distant targets with pinpoint accuracy and incredible destructive power, all while firing projectiles that cost far less than a missile. However, in practical terms, the performance is not yet as consistent as the theory suggests. High rates of fire lead to rapid rail wear, heat buildup can cause warping, and the enormous energy requirements limit how often and how quickly a railgun can fire in real-world scenarios. Some prototypes have achieved rates of one shot every few minutes rather than the sustained barrage that military planners ideally want. Safety is a core consideration in railgun design. While the absence of explosive propellants and warheads dramatically reduces certain risks, the sheer amount of electrical energy involved introduces new dangers. To mitigate these, railguns incorporate multiple safety layers. The capacitor banks are equipped with rapid discharge systems that can safely bleed off stored energy in case of emergency, preventing accidental firing. Physical and electronic interlocks ensure that the weapon cannot be fired without specific conditions being met, such as barrel alignment and crew clearance from high-voltage zones. Cooling systems are also part of the safety framework. Not only do they maintain operational performance, but they also prevent dangerous overheating that could lead to structural damage or sudden rail failure. Crew members are trained to respect the lethal potential of both the projectile and the stored energy, with strict protocols governing who can enter maintenance zones and when. The electrical environment around the weapon during firing is so intense that sensitive electronics nearby must be shielded, and personnel must wear protective gear in certain situations. Automated diagnostic systems continuously monitor the health of the rails, capacitors, and power circuits, shutting the system down instantly if anomalies are detected. The unique selling points of a railgun are compelling. First and foremost, the cost per shot is much lower than comparable missile systems once the weapon is operational. While a modern guided missile can cost millions of dollars, a railgun projectile, essentially a solid piece of metal with some guidance fins in advanced versions, might cost only tens of thousands. This offers a potential for huge savings in sustained engagements. The speed of the projectile makes it extremely difficult to intercept, and the lack of an explosive payload means it can be stored and handled more safely on ships. The weapon's versatility is another key advantage. It can be used for long-range bombardment against shore targets, anti-ship warfare, and even missile defense, since a railgun shot can theoretically hit incoming threats with almost no warning time for the target. The psychological impact of deploying such a weapon should not be underestimated either. Just knowing that an adversary has a weapon capable of hitting you from over 100 miles away in seconds could alter strategic calculations. Additionally, the railgun is a step toward the broader adoption of energy-based weapons in militaries, serving as a bridge between traditional kinetic arms and future systems like high-energy lasers. Then there's the price, and this is where enthusiasm often meets cold reality. Developing the railgun has already cost hundreds of millions of dollars, with some estimates pushing into the billions when factoring in decades of research, testing, and ship modifications. Each individual railgun system requires massive power generation capacity, which means only certain classes of ships can even consider mounting one. In some cases, entire vessels would need to be designed from scratch to integrate the weapon effectively. Maintenance costs are another factor. The rails themselves degrade with use, requiring regular replacement, and the cooling systems consume significant resources to operate and maintain. While the projectiles may be cheap, the infrastructure to launch them is anything but. Critics argue that for the price of developing and deploying a fleet of railguns, a navy could purchase a much larger number of proven missile systems with similar or greater real-world effectiveness. The U.S. Navy's recent decision to scale back funding for railgun development in favor of hypersonic missiles reflects this tension between potential and practicality. In conclusion, the railgun stands as one of the most fascinating weapons of our time, a true testament to the ambition of modern engineering and the enduring human desire to push technology to its limits. On paper, it is everything a military strategist could want: long range, high speed, low cost per shot, and safe to store. In practice, it is a complex, expensive, and maintenance-heavy system that still faces major obstacles before it can be fully deployed in combat. The future of the railgun will likely depend on advances in materials science to extend rail life, breakthroughs in shipboard power generation to support sustained fire, and continued political will to fund development in the face of competing priorities. Whether it becomes a staple of naval warfare or a cautionary tale of technological overreach remains to be seen. For now, it is both a marvel and a question mark, a weapon that embodies the promise and the pitfalls of chasing the cutting edge. If those challenges can be overcome, the railgun could indeed redefine the battlefield. But if not, it might be remembered as one of the most spectacular what-if stories in the history of military technology.